Okay, so let's continue with section 18.4, talking about the concept of an electric field. Okay, so where this comes from is, let's say you've got a charge Q situated here, and you bring another charge in nearby. You know from the previous sections that we're going to either have a force pushing this charge away or pulling it closer, depending on the direction of the field, or the charge polarity of the charge. So this means no matter where you put this charge, you expect it to be pushed away or pulled towards. So we can think of this as there must be some sort of force field emanating out from this charge. So we can think about it that way. So we call this the electric field. Okay? And so what this is describing here on the left-hand side of the screen, the concept of a field is just to say, okay, well, we know that the force between two charges is Q1, Q2 over R squared. But if we just drop in a charge, so like a test charge, just plop over on the right-hand side of the screen here, drop a charge over here, we can calculate that the force between the two charges, the force is going to be K Q1 Q2 over R squared. So we can define the electric field generated by the test charge Q, which I'll rewrite as capital Q, Q, and little q here. So Q1 is our test charge. And what this says is that the electric field then generated by the charge Q, we can think of it in terms of some force, the force between it and some test charge, divided by the test charge. Okay, and what that does is allows us to write K capital Q little q test charge over R squared, and then we're dividing by Q, so that cancels the little q out, and so we're left with KQ over R squared. So then the electric field strength, if we go back to the left side, is defined, the electric field itself is determined by the force experienced by a test charge divided by the charge of the test charge, because it doesn't matter what the charge of the test charge is, we want to know what the strength of the capital Q is. And it will respond, whatever charge you put in there is affected by this electric field. So this is a way to cancel out any other charge you might put in there and look at the characteristics of a single charge. Okay, and so what they're showing here then is that the electric field is force divided by charge, and then it works out to be that the electric field generated by a charge is just Q divided by R squared, its own charge, and then that gives you a map of sort of its strength at any given point. And then if you plopped in a charge at some other point, you'd be able to calculate the force by taking this equation 18.11 and just saying that the force is the electric field times the charge that you plop in there. And now we have a way to determine the force on any charge in the vicinity of another charge. Okay, so to recap, the electric field is just, we imagine a charge Q here, and then we imagine this field going out, so that whatever charge we plop another charge somewhere around here, we can calculate the strength of the electric field at any of these points, because the electric field itself is defined only in terms of the charge of the main charge sitting there. Okay, so here's an example here. If you want to calculate the electric field of a point charge, so let's say we want to know the electric field due to a charge of 2 nanocoulombs, which is 2 times 10 to the minus 9 coulombs, that's what a nano is, at a distance of 5 millimeters from the charge. Okay, so what are we doing? We've got a charge Q, and we want to go a distance 5 millimeters from it, and we want to figure out what's the strength of the electric field at that point. Okay, so we know what the electric field is generated by the original charge here. There's our charge. It's going to generate an electric field. What's the strength of the electric field at that point? So we know the charge is 2 nanocoulombs. We know we're 5 millimeters away from it. So we can just put 2 times 10 to the minus 9 coulombs and 5 times 10 to the minus 3 meters in there, Q over R squared, multiplied by our constant, and we get the electric field strength at that point, a distance 5 millimeters away, is 7.19 times 10 to the 5th newtons per coulomb. Okay, so there you go. And if you multiply now by a charge, you'll see that cancels out that coulombs, leaving you with newtons, and that's how you can determine the force on another charge that's put in there. Okay, so by definition, yeah, okay, so what they're saying here is that if this is your charge Q and you go a distance 5 meters away, doesn't matter where you are, as long as you're 5 meters away, the strength of the electric field at that same distance is the same, at least from a point charge. Okay, if it's positive, that means it's pointing away from the charge Q. So we could draw our electric field as pointing away from the charge. Okay, let's do example 18.3. We want to calculate the force exerted on a charge by an electric field. So if we go to this previous question, all we did was determine the electric field. Now what we're doing is we're dropping in another charge at that point and determining what the force on that charge is. Okay, so question is, what is the force on the exerted on a point charge of 0.250 microcoulombs? So a micro is times 10 to the minus 6 coulombs. So we're going to do the same thing here. We're going to take the electric field we just calculated, and we're just going to multiply it by this charge, 0.250 microcoulombs, and that'll tell us the force that this one experiences. So the solution is, you just take that charge, we've got our previous electric field at 5 millimeters away, just plug those two things in, multiply them, and we get 0.18 newtons. Boom, we calculated a force immediately. We could, if we knew the mass of that charge, we could say F equals ma, take this force divided by the mass of the charge. Let's say it was a proton. We could just put the mass of the proton in, and we could calculate the acceleration and how quickly the charge would move, and then you could calculate how long it would take to go from one point to another if you wanted to. Okay, so, and then again, you've got these PHYS interactive simulations, so make sure you're doing those. You'll see those in the book on the Canvas website. Otherwise, you can just go to this website here. Okay. So section 18.5, so the way we characterize the strength and properties of an electric field are with lines that are always pointing away from the charge, okay? And if it's a positive charge, the arrows always move away. If it's a negative charge, as you can see right here, the arrows are always pointed towards it. So we call positive charge a source, so this is a source. And negative charge is called a sink, okay? So water comes from a source and goes down a sink. Same thing with charge. We can think of the electric field as emanating from a positive charge and ending on a negative charge. Okay, so let's see. Yeah, we just got two. These are the same diagrams, both of these showing the same thing. There's nothing different about them. This one, they just drew more arrows for some reason. Just to look cool. The number of arrows don't really matter along the line. What does matter is the density of arrows around the line. So if you have more arrows, more lines in a area, so these are closer together, that means the electric field's stronger. These ones over here, so I could say that this field is weaker than that field just by looking at it. Okay, so that's a choice we've made as scientists to a way to draw an electric field to demonstrate its strength is to increase the number density, the number of lines that you see. Okay, so important things to take away from here. Lines always come away from a positive charge and always end on a negative charge. And that's the most important thing. Okay, so again, what are these lines showing? These lines are showing you where an electric field line, as you move along this line, or towards this, your electric field is changing in strength by r squared, 1 over r squared. So that's what these lines are allowing you to do. Then if you drew a line around in a circle perpendicular, the strength of the electric field would be the same all the way around. Okay, so these are just some facts. All right, so example 18.4, this is a tricky example because the diagram doesn't make a lot of sense. But what it's saying is it wants you to find the magnitude and direction. Remember, an electric field, since we've got lines and arrows, it's going to be a vector here. If we want to determine the magnitude and direction of the total electric field due to the point charges Q1 and Q2 at the origin of the coordinate system in the figure below, okay, that's what we want to do. So we've got charge 1, which is 5 nanocoulombs, and we've got charge 2, which is 10 nanocoulombs. and it looks like charge 1 is 2 centimeters away from the origin, and Q2 is 4 centimeters away from the origin. And so what we want to do is, the strategy here is to ignore charge 2 and just look at charge 1 and calculate what its electric field is at this point at the origin. So all we're going to do is that the electric field is K and then Q, 5 nanocoulombs divided by R squared. We're 2 centimeters away, 2 centimeters squared. Okay, so you take K times 5 nanocoulombs divided by 2 centimeters squared, and then you get the electric field. If you do that, here it is, down here, 1.124 times 10 to the 5th. 1.13 times 10 to the 5th. They rounded up here. 1.124 took it to 1.13 for some reason. Okay, so if you do that, so what is this diagram showing here? This is really confusing, but we have a charge, and then we're moving 2 centimeters away from it, and then we're asking what is the strength of the electric field here? And then we calculate that the strength is 1.13 times 10 to the 5th newtons per coulomb. That's the strength of it. Now we can represent that strength with a direction and an arrow. And so that's what this vector is showing here, is representing that the length of this arrow is corresponding to the value of 1.13 times 10 to the 5th, and it's also pointing straight up. So that means if you put a charge here, that's the direction that the force would feel. So that's our first charge, and now we're doing the second charge, which is over here, and it's 10 nanocoulombs, and it's 4 centimeters away. So what we're going to do is go 4 centimeters away, and let me just draw this as a dotted line too. We're going to go 4 centimeters away and calculate what that is. So again, we just put K and then Q, 10 nanocoulombs divided by R squared, plug that in, and we can get our E2 here. Now E2, again, we're drawing it because we want to know at this point at the origin, the length of this arrow is 0.56 times 10 to the 5th newtons per coulomb. That's representing that length. So it's a little bit shorter. I should draw this one a little bit longer. It's a little bit shorter because it's less of a magnetic field. Now, if you put two of these charges together, what's going to happen is their electric fields are going to combine. So if you put a third charge in there, it would get a net force from both of them. And so we want to know what's the net electric field, so then we can just calculate then what the force is on a third charge if we plop it in. So the way you do that is to take this vector here, okay, and then bring it over, whoop, and do your head to tail method. So when you add this vector plus that vector, we get this vector. And so that's what this vector here is this as the y component, this as the x component, gives you a triangle where that's the y component and this is the x component. So there's our vector here. Our E total vector is the sum, E1 squared plus E2 squared square root will give you the length of this vector. And so that's what this is right down here. If you have that as your x and that as your y, and then you get your hypotenuse. It's x, y, z. Z squared is going to equal this, well, z is going to equal the square root of x squared plus y squared, okay? So we just got our triangles here. All right, so then, does it ask the direction? It does. Find the magnitude and direction. So it does ask the direction. So the magnitude would be the length of this vector. The direction is going to be the angle here. And so it's just a triangle. So if we know all three sides of the triangle actually, so you could figure out any angle you wanted. In this case, we're just doing, since we know what E1 and E2 are, the x and y, we can just relate them the opposite over adjacent side. So the opposite over the adjacent side of this triangle. We can get that the inverse tangent, or the tangent of theta, is the opposite side, E1 over E2. And then if we want to know what is the angle theta, we're going to take the inverse tangent of E1 over E2. And that's going to give us the angle, which is 63.4 degrees. And again, you should work through all these yourself. Okay, so this is an example of, we've got two electric fields. They're adding together, and we want to get the total net sum of the two vectors. So we have to figure out each electric field individually and then add them vectorially, okay, in 2 dimensions. Okay, so then There's some discussion here. Yeah, you can read that. That's a little bit more advanced stuff we're not going to do, but it gives you an idea. Figure 18.25 is down here, this main figure, and what it's showing is you have two positive charges, and it's kind of showing you how the fields interact with each other. Since the two charges repel each other, the electric fields diverge away from each other, and you end up with this area where there's no electric field between them. And if you put another charged particle in there, it wouldn't experience a force, or if you put something else in there. Okay, so what this graph is showing is, like, let's say at this point P, it's showing that the net electric field is due to this combination of E2 and E1, and down here the net electric field there is E1 and E2. So this is really confusing because what it's showing is that at any given point, right, this overall curve is given by the tangent of the electric field strength. So at each of these points, the arrow that they're drawing, like this arrow, the length of it is trying to represent the strength of the electric field at each of these points. So these arrows that they're drawing here, they don't really mean anything with respect to the actual picture. They're trying to represent how they determined the shape of this arrow, and it's because of the way the electric fields add up to give you this net force all the way around. So it's a little bit of a confusing picture, but if you spend a little bit of time on it, I think it'll make perfect sense to you. Okay, and then we've got a couple of really cool pictures here. Same type of graph for negative charges like we just looked at. Notice the arrows are sinking towards the minus sign. They're not leaving it, like if we go to the positive charges up here. These positive charges, the arrows are pointing away from the sources. And then if we put a positive and a negative charge here, they will source from the positive charge and sink to the negative charge. Now notice the lines are complete. They start and end on charges. So this will always be the case. These lines always begin and end on a charge. You will never have, like this line, eventually here will reconnect, okay, wherever it goes to. You won't just have a line that just disappears off into wherever. So that's an important thing that we'll talk about down the road too. Okay, so here's your rules. 1, 2, 3, 4, 5. Make sure you read these. The field lines that we're just talking about, they must begin on positive charges and end on negative charges. Okay, the number of field lines leaving a positive charge or entering a negative charge is proportional to the magnitude of the charge. So, like, if this charge here, if we drew the same one, but, you know, weaker, it wasn't as strong, then I would draw the arrows, the density of the arrows coming off of them as fewer. And then I could say, well, that charge, this charge then is less than the other one. Okay, the strength of the field is proportional to the closeness of the field lines. More precisely, is proportional to the number of lines per unit area to the lines. So this number 2 and number 3, they're related to just a rule about drawing them. There's no, you know, set in stone way to draw these. If you just want to describe the strength, then you can draw 2 with different numbers of lines and densities to represent the different charges. Okay, the number 4, the direction of the electric field is tangent to the field at any point in space. That's what this is trying to say. The electric field is tangent, okay, always to the electric field. The direction of the electric field itself is tangent to the field line, okay? And then number 5 is the most important. Field lines never cross, okay? So these field lines, you can see they always begin and end on a charge, and they don't dip around or whatever. And that tells you something really important about it, what's going on. Okay, and then you get another FET here. Make sure you go through that and just kind of play with it. You got moving point charges around and seeing how their lines respond. All right, and then we get into some weird stuff. Electric forces in biology, not super important, but DNA is highly charged, and the way all the stuff hooks together is due to these electrostatic forces. You've got the ACGT in the DNA, the base pairs that make up your DNA. It's got 2 times the fundamental charge, or the charge on an electron, per meter, right? So this is well, per this much of a meter, per billionth of a meter. Okay, so anyway, it's about a nanometer apart, blah, blah, blah. So, yeah, this is interesting. We talked about the polarity of water molecules before, why the water is dipping away a little bit. And then 18.7, conductors and electric fields in static equilibrium. So a conductor, remember, allows the electrons to move around. They have free charges, move easily. So electrons that are not bound or trapped in an atom. Blah, blah, blah. Let's go through here. This stuff isn't super important. A conductor placed in an electric field will be polarized. So let's say you put an electric field somewhere. You've generated an electric field with a voltage source or something, and you drop a conductor in here. What does it mean to be polarized? It means you've separated the sides out into two areas. So the positive and negative charges aren't mixed anymore. You've got the minuses all on one side and the pluses all on one side. So again, that can be something that could be beneficial in engineering application, which is down here when we're talking about printers. So we've got some applications here with laser printers. So what's the laser doing? The laser is erasing charge from a roller, and it's leaving only one area charged, and that's where the character is, and then it rolls that onto the paper and deposits the image that you want to see. So that's why they call it a laser printer. That's what the laser is doing. You've got inkjet printers, electrostatic printers that are you're trying to sprit charged particles onto the paper. Okay, so let's go back to here. If you take a conductor and you put it in electrostatic equilibrium, the electric field inside the conductor is 0, which is cool. Just outside the conductor, the electric field lines are perpendicular to the surface. You can see, boom, boom. That means a 90-degree angle where it leaves off. You're not going to get an arrow shooting off like that, which, since field lines can't cross, they have to come off this way. Okay, and then 3, any excess charge resides entirely on the surface of the conductor. There's no charge on the inside of the conductor. Okay, so down here we've got an example of a capacitor, which we'll talk about later. Capacitor, you have two plates, and they're parallel plates. They're parallel to each other. You've got, this is positively charged, and the other side is negatively charged. You get this is a way to create a nice uniform electric field. But you have what are called fringe effects or edge effects here when you get outside of the parallel plate capacitor. It's kind of like a sandwich, and you've squished it too much, and now you got jelly leaking everywhere, okay? Since you don't have these field lines able to connect easily, they kind of leak out like that because they don't have a line to immediately jump down to, and it gets crowded in there. Okay, so this is just an interesting thing. Earth has an electric field, okay? There's electric fields all over the place. Lightning is an example of that. When you get two charges, between the clouds and the ground, you get charge separation when a storm comes in, and then eventually the energy between the two is high enough to ionize the air, and then it just releases all the energy to the ground, which is pretty cool. Okay, and then there's this little aside on electric fields on uneven surfaces, and that just, again, they always have to come off perpendicular so that the lines never cross, and that's pretty cool. Otherwise they cancel out, and then you end up with this weird stuff. Okay, so, and then you've got your applications of conductors. Now, there's a cool thing called a Faraday cage, which is also an elevator. If you've ever gotten an elevator, you lose your cell phone signal. Now, you might think, maybe there's something special about the elevator, but your phone works in the building, so it's not like you go into some place where there's more building. What happens is your elevator is a Faraday cage. It's a conductor on all sides, a closed conductor, and so the electromagnetic fields that come in from space to talk to your cell phone, they actually get absorbed into the walls of the elevator, and so that helps to attenuate the signal. And blah, blah, blah. Same thing if you're in a car, it gets struck by lightning, or a plane gets struck by lightning. Generally, you'll be safe. Most of the time, there's not a problem with that. You might blow out your tires or something. But that's the benefit of a Faraday cage, and you should Google that. There's some weird people doing some weird stuff around Tesla coils in suits of armor and stuff. And also, if you work on high tension power lines, you wear this suit of armor, like this chain mail like suit that protects you from feeling the effects of the energy, because you give a path for it to leave through, stay on the surface of your body. Okay, and then this is a pointed conductor, and so the pointed conductor, you get very strong magnetic field at the tip. So these devices you can use to charge stuff up or to take charge off or whatever. And then they have an example of a lightning rod on top of a church here or a house or something, so that if lightning strikes, it finds that path first rather than the wood that would burn or something. Okay, we've got a Van de Graaff generator here, and a couple of Tesla coils here in this picture, doing something weird, I don't know. Okay, Van de Graaff generators. We've talked about that in the first lecture. There's just a belt here that rotates, and then you've got a thing here that it's scraping against and just pulling charge off of it. So it ends up getting a net positive charge up here, and then what you can do is, touch it and charge your hair up, or send your energy off to somewhere to accelerate them, whatever you want to do. Blah, blah, blah. And I think that's going to take us to the end. This is an air filter here. So this is the example of filtering air. Yeah, okay, here's an example. Acceleration of a charged drop of gasoline. So let's say you have a drop of gasoline. It's got a mass, and it's given a charge. So what they're saying is, if you don't ground the pump when you go to pump your gas, you could charge up the gas, and then if it's charged, it could get dispersed where you don't want it. So we want to calculate and see if this is something we should worry about. So first of all, they want us to calculate the weight of the drop. Then they want us to calculate the force on the drop. If there's an electric field showing up of this amount because of, someone was rubbing their head with a balloon or something. And then what would the acceleration be because of that charge? So part A just wants us to figure out what's the weight of the drop. And you may remember weight is just the mass of the drop plus or times gravity. F equals ma. In this case, A is G, M is M, and the force we call the weight. So you do that, you get this many newtons. So gravity doesn't pull on this drop of gas with very much oomph. That's a pretty weak gravitational force. But if we put this electric field, 3 times 10 to the 5th newtons per coulomb, on something with that charge, 3 times 10 to the minus 19 coulombs, remember, the force of the electrostatic force is 10 to the 30 some times more powerful than the force of gravity. So if we already have a really weak force of gravity, and we have even a small charge, we're going to get a big difference. So let's calculate what the force would be then on this thing. The force would be F is Q times E. So we are given the charge 3 times 10 to the minus 19. It's twice the fundamental charge in the electric field. So we just plug all this in. The force then is the charge that we have times the electric field that we're given, and this would be the force due to the electrostatic force from a charged particle. So now we compare these two forces together. See, well, okay, they're actually both of the order of 10 to the minus 14 newtons. This one's 3 or 4, this one's 9 or close to 10. So this electrostatic force is about twice bigger than the force of gravity, which means you're going to have a net force above gravity because that force is bigger. So it says here discussion for this. So that while it's a small force, it is actually greater than the weight of the drop. So that's a problem. So for C, we want to calculate the acceleration. Well, F equals ma. The net force on this is going to be the force, the electrostatic force up minus the weight down divided by the mass. And if you put that force in that we calculated minus this force, we get an acceleration of 14.2 meters per second squared. That's pretty fast. That's faster than when you drop something. So it's going to splash some gasoline somewhere. And that's enough to carry the drop to places where you might not wish to have it, okay? So that's an example of how you could calculate the electrostatics involved, or the forces involved in a charged particle. All right, and that's the end of that.